And that drive to explore, that drive to know, when you learn why the sky is blue, when you learn why the sun creates all that energy, it's cool. It scratches a certain itch that is just really, really satisfying.
You're listening to Good is in the Details. I'm Gwendolyn Dolsky.
And I'm Rudy Sallow.
And Rudy, what is this show about?
You're putting me on the spot today. This show is about...
It's about time I put you on the spot.
It is true. This show, what we like to do on this show is we like to take experts and we like to learn about what those experts tick. No, this is terrible. Make sure you delete this. This show is about trying to apply the ancient, old school tenets of philosophy and seeing if we can take some of those teachings and apply it to this crazy world that we live in. That is current events and some self-help and how to be a better parent and how to navigate social media. So we're trying to take some of the old and applying it to some of the crazy new. And sometimes, I'm helpful and I throw in some legal stuff and some other comedy related type stuff, even though I'm not very funny because no one has ever responded on the show that I'm funny, and I still take offense to that. But this show is really about talking to the experts, applying some philosophy, throwing in some law, and trying to become better people. And that, to become a better person, doesn't that take learning how to be good in the details, Gwen?
Absolutely. And listeners, I think that we need a review that tells Rudy he is funny.
Be nice.
Just do it. Yeah.
On
Facebook
nice.
Or tweet it out. That's totally fine.
Just one. Yeah. That's all I need. I don't need a lot. I don't need a lot.
But yeah, that's what we like to do. We're learning what we didn't know in the spirit of Socrates.
Socrates.
Yes.
From now on, I know what to say. You know what our show is about? Socrates.
Socrates. All right.
Socrates.
And this episode is very cool. So, I teach a class, Ethical Considerations in Technology, and our guest today is NASA engineer. She worked on the Mars Reconnaissance Orbiter and the Kepler project, Tracy Drain. I saw her TED Talk. I'm going to link it in the show notes. But I think that this is a show for everyone because we are talking about space exploration and we're talking about the mechanics of it. But at the same time, the underscoring idea is just this notion of curiosity and human excellence and how her work is really about the exploration of that and what is possible. And it's very exciting to not only hear about her projects, but also what engineering and space exploration can tell us about everyday life.
And what I have, because I'm selfish,
right.
I want you to know, everybody should know I'm selfish. What I got out of the show, a lot of that stuff, Tracy, excellent guest, so impressed by her and everything that she's done. But what I really wanted to talk about is aliens. And this people have made, I get made fun of in this during the episode. I get made fun of on Instagram because of this. But I legitimately ask one of the most important questions. Are we alone? And what the impact of the answer to that question could have on humanity. And of course, you bring some philosophical teachings regarding that, Gwen. So it's a wonderful episode.
Okay, so we get the answer about aliens.
We do.
That's perfect. Okay, and let's talk space exploration. There we go. What do you think?
Perfect.
Thank you for joining the show. It's so exciting to have you on. I would love if you could start out a bit with your background, and then I want to know, out of your projects, so this might be hard to narrow down, was there one that was the most meaningful for you and why?
Okay, so my name is Tracy Drain. I am a flight systems engineer at the Jet Propulsion Laboratory. And in my background, I studied mechanical engineering in school, both for my bachelor's degree and my master's degree. I've been an employee now as a systems engineer at the Jet Propulsion Laboratory for the last 20 years, starting to get a little old now. And in that time, I have had the very great fortune to get to work on 5 different missions. One is the Mars Reconnaissance Orbiter, which is still in orbit around Mars. The Juno mission, which got into orbit at Jupiter in 2016 and is still orbiting there. In between there, I worked on the Kepler mission, an exoplanet hunting mission. And then Psyche, just for a couple of years. It hasn't even launched yet. That one's going to go off and study an asteroid in the main belt. Now I'm the flight system engineer for the Europa Clipper mission, which is going to launch in 2024 and head off to study that really cool moon of Jupiter. And it is really, really hard to pick one of them. So as an engineer, right, I'm not working on the science side of the house, but all the things that we do are to enable the scientists to get the data that they need in order to go answer really cool questions about our solar system and our universe. And the one that I think that has been the most paradigm shifting based on what they've discovered is Kepler, because we knew about a lot of other planets that had been discovered before Kepler was launched. But Kepler's mission was to determine how common planets were in our galaxy, and also to try to find some planets that were Earth-like, at least in a couple of ways, in terms of their size, kind of Earth-sized planets, and in terms of being close enough to their star and not too far away that they could theoretically be in a habitable zone around the star. And now, with Kepler's data, we kind of understand that there are literally billions and billions and billions of planets in our galaxy. I think the way that they have broken it down is to say that it's not true that every star has a planet, and it's not true that, well, so not every star has a planet, but on average, there is about a planet for every star, right? Some have lots, some have perhaps none. But with our galaxy containing somewhere, I've seen estimates from between, 1 to 100 billion stars, that means there are roughly that many planets in our Milky Way galaxy, which is just crazy. Like anywhere you look in the plane of the Milky Way galaxy, the sky is literally dripping with planets. It's ridiculous.
And Tracy, I know we're going to get into this when we talk about the most important question on this podcast, but it's going to be the most important question. I'm telling you that right now. So Kepler helped learn that there's billions and billions and billions of planets, but how many of them are Earth-like?
What I remember reading is that the number of planets, and like I've been off the mission for a few years, so please everyone go Google fact check. It's really easy to go learn what the Kepler discoveries are. But there were at least, I thought, a couple of dozen that were in the Earth size range, like 1 to 2 Earth masses, and that were within the habitable zone of their stars. Now, the tricky bit, right, is that we don't know if they have an atmosphere, right? And you really kind of need an atmosphere if you want to host life as we know it, Jim, because you need protection against the ultraviolet radiation that's coming from the star. If you want to have liquid water on the surface, you need to have the right pressures and all of that jazz, not just temperatures. But those are the ones that are starting to look like there's some potential there. So yeah, go fact check. The numbers are out there.
Do you remember when you were young, the moment when you started to become fascinated with astronomy or with planets, and you thought, okay, this is something that I want to pursue? Was there a film or a story, or where you thought, oh, that's a possibility, or that's really cool?
I think that because I was raised by a mom who really loved science fiction, I was always exposed to the idea of this fantastical future world of space exploration and always fascinated by the kinds of things that could be out there. But I do remember this one particular moment when I was in high school, and it was between my junior and senior years over the summer. Some of us in Kentucky got to go to this program called the Governor Scholars Program. And they picked, several kids, and we went to one of 2 different campuses, and you got to choose a quote major, unquote, where you would take like an hour or 2 of these classes and get to study with other kids, whatever. And I chose astronomy. And they took us in the middle of the night out to this dark place. Like I had grown up in the city, Louisville, Kentucky, where there's so much light pollution. You can see stars, and I thought that seeing stars was cool. But it wasn't until that incident where they took us out to where it was actually like really dark, and I could see the Milky Way. I'm like, wait, but what is that? You can see that like with your own eyes, and you don't need time-lapse photography? Like what? And being able to have our astronomy teacher tell us about why you could see the Milky Way galaxy and give us star maps and show us things around the sky I was hooked. And even before that, I was always thinking a little bit about potential career in space. But from that point on, yeah, that was it.
Tracy, as a part of your, the information that you could find out about you online, one of your interests in space says that you were a big science fiction fan, Star Wars, Star Trek, Battlestar Galactica. However, there is a major difference between Star Wars and Star Trek, right? And the difference is Star Wars, much like Game of Thrones, is more fantasy versus Star Trek, which technically could still happen because it's still in the future. Do you agree, or am I sounding like a crazy person?
Actually, that's a little different from what I personally feel is the main difference between Star Wars and Star Trek, especially when we think about The Next Generation, which was my jam when I was growing up, right? I thought of Star Wars as kind of like an action film set in space. You had the forces of good and evil who were battling it out, and there were chase scenes and blowing stuff up, and it had that flavor to it. For me, the thing that I love the most about that era of Star Trek is that it was about variety of humans from different backgrounds working together to explore space and peaceful missions. And they always came across these weird things that were going wrong, and they always tried to find non-violent solutions to things, even though it took me a long time to really realize that that's what I saw as the heart of that show. I love that about Star Trek. And so everyone always has these arguments, right? What do you think is better, Star Wars or Star Trek? I have always loved Star Trek more for those reasons.
In working in JPL and in the 20 years that you've worked, are those environments more like Star Trek, or are they more action adventure like Star Wars? I'm really curious. I just want to know what it's really like. I've seen The Martian. You have the scenes with Matt Damon on Mars, and then you have the scenes of JPL and the problem solving. There's great scenes like that. And I know, trying to separate fiction from fact here, but that's my insight into your world. So I'm just trying to get a little bit more of a flavor from somebody on the inside.
Yeah, I love that. No one's ever asked me the question that way before. But I think it is definitely more like Star Trek. Like, those scenes where they're trying to get somewhere and there's something wrong with the work drive. And so they have to come up with all these creative solutions in order to get there. When we're doing anomaly resolution, things are going a little bit sideways on our spacecraft, and we have to figure out what happened, why did that happen, what can we do about it, and sometimes the clock is ticking to get it done. It feels like that, like you're on the bridge or you're in the engineering room trying to come up with a solution to keep your mission going. So Star Trek all the way.
That leads me to one of my questions about what is the disposition of the engineer? So I'm curious about the work that you do. What are some things that the general public can learn about life from problem solving in engineering?
Oh, yeah. I love that question too. And especially the type of engineering that I do, which is systems engineering, meaning you take this big complex thing, it has a lots of moving parts, and you're trying to go and accomplish some high level mission goal, like get some science, right? And there are so many different focus areas, like thermal, keep the spacecraft from getting too hot or too cold, telecom, be able to communicate with the ground, attitude control, get your spacecraft pointed in the right direction. And there are people who focus in all those different areas, but a lot of times when something's going wrong with the spacecraft, it's something that involves multiple areas. And so no one expert is going to be able to come up with a response that is going to be good for the overall spacecraft and the instruments, what we call the flight system. And so a systems engineer needs to be able to understand enough about all those different systems to communicate with the experts, translate back and forth between the experts to the people who are going to be like, what are you talking about over there? And come up with a balanced response that is going to be good for the whole spacecraft. And I think in that systems engineering kind of job, communication is so important. And it's not just about understanding and communicating, articulating the technical detail. A lot of times it's about understanding the human beings who are doing the work, because you can be so laser focused on your own area that you have blinders on and it's difficult to see other perspectives. When we're under the gun, like stressful situations, trying to get something done, the clock is ticking, people can get a little heated. So it's good for people to have the ability to remind people we're all trying to do the right thing. These are the knobs we have on the table. We're going to choose a solution that isn't going to make everybody happy, but as long as the spacecraft is safe, it's okay. So there's those basic kinds of skills of how to communicate, how to see multiple perspectives, how to listen and try to pull the right things out of everybody, and then build a consensus in a timely manner that can be applied to a whole bunch of different things in life.
I got a really quick question for you, Tracy, and this is going to give you a little bit of a window into my thinking about myself. I'm terrible at math. I'm terrible at science. And because the reasons why I'm terrible at those things is because I feel like you can't, pardon my phrase, you can't BS them. Like they are what they are. Like math is math, science is science. However, if you're in law and you're in politics or you're in your history, those things, those are kind of squishy. You can play around with that. You can play around with perspectives. Am I right or am I wrong? Is science and math? Because what I'm hearing from you is, well, no, there's an engineer here that has this perspective. They have this experience. So like what I'm trying to ask you is can I become an engineer? Is it too late for me? Can I play around with some stuff? I'm fascinated.
I don't know what in the world you would build, Rudy. You're fascinated.
Don't get me started. There's not enough time. Tracy's on a time constraint. Whole other podcast.
That is so great. So there's two answers to your question. Number one, it's hilarious that the things that you didn't like about math or science is that they were so concrete, right? That's actually the thing that I found the most reassuring. When I'm in learning math class, like you add 2 and 2 and you get 4, like that is the answer. And I remember the first time I was standing at the blackboard, I have like a little bit of PTSD from this. When I was a little kid and we were supposed to be doing subtraction, and subtraction was quite new. And I had apparently copied the problem wrong, and I put the smaller number on top and the bigger number on the bottom. And so I tried to do the subtraction, and like my brain was exploding, like it wasn't working, and I'm starting to freak out a little bit. And the teacher comes over and she's like, no, it's totally okay. You just copied the problem wrong. Do this. And then she goes, you will be able to answer that problem later, but we haven't gotten to negative numbers. And I'm like, oh, negative numbers, like this whole new window on the universe has been opened. But she restored my faith in math because it's supposed to make sense. It's supposed to be repeatable. Like 2 people should be able to do the same problem and get the right answer. I love that about math. The reason why the answer is not exactly the same when you get to engineering complex systems is because there is not a single right answer. And I'll say it this way, like say we have a spacecraft and we're trying to communicate down to the Earth. And we have this dish on the ground listening to our spacecraft. We have a much smaller dish on the spacecraft aiming at the ground. And there are 2 different ways that you can make a really strong telecom link. You can have a lot of power in your signal, so you're essentially screaming at the Earth and it makes it easy to pick up your signal. Or you can have a fainter but more tightly beamed signal and then point it really, really well. Like imagine you have a light bulb. In the first case, it's a light bulb. If your light bulb is really, really, really bright, then you can pick it up on the ground, even if you're not aimed very well. If you have a laser pointer and you're aiming it at that dish and you're off a little bit, you're not going to pick it up on the ground. And so when we're trying to make a spacecraft that communicates well, you can either lots of power in your telecom signal or less power and aim it really well. And either of those 2 things will work, but there are limitations. If you're a solar-powered spacecraft and you need lots of power just for your telecom system and to keep the spacecraft warm and to run all your instruments and your solar arrays have to get bigger and bigger and bigger, and that makes your spacecraft heavier. You need a bigger launch vehicle. So overall, that might not be the best solution. But if you, instead of using lots and lots of power in your telecom signal, you use less power, but then you point your spacecraft really well, now you just need a really fine-tuned guidance and control system to be able to point very well. Sometimes, depending on the spacecraft, it's easier to do that. And so you need different perspectives. You need to look at the big picture. You can choose either answer. It's just you have different collateral things to deal with depending on the choice that you made.
Back to Rudy, what you're thinking is that while engineering and math and science are objective, the expression of it is value. In order for your work to work, it has to be mathematical, it has to be based on science. But the fact that we spend all of this human energy into going out into space, that's a value, which leads me to my question. Why do we do space exploration?
Yeah, great.
What's it for? If we were to ask the lay person, what is it for? What do we do it for?
Mm-hmm.
Now
I
we're
have
talking.
2 more answers for you.
This is good. Now we're getting into the good stuff.
I mean,
Gwen's leading me up. She's teeing me up here.
This has nothing to do with you. I actually have my own motives because I'm thinking of Aristotle a bit, that he talks about the if you keep asking people, well, what do you do this for? What is it for? What is it for? Eventually people come to this notion of eudaimonia, which means excellence. And I think that space exploration is in that ballpark. So, but that's me, the philosophy professor, saying that. So I would love to know, if somebody's asking, what are we doing this for? Okay, so that's all really cool, but why? How would you?
Why? I have 2 different answers for people. And it's because in my experience, one answer resonates more with a certain type of people and one answer resonates more with a different type of people. There are people, let's see, I'll say it this way. I think that humans kind of come hardwired with this natural driving sense of curiosity, right? I've actually given a little TED Talk on this topic where you look at little kids and you see them running around exploring their world and they learn something new and you can just see their little eyes light up. It's exciting and fun and wonderful for them just to learn, not just to eat something that tastes good or to be warm and, all the things that are necessary for basic health and happiness, right? And that drive to explore, that drive to know, when you learn why the sky is blue, when you learn why the sun creates all that energy, it's cool. It scratches a certain itch that is just really, really satisfying. And there's a group of people who look at space exploration from that point of view. And even if it was just pure adding to human knowledge, they would think it would be totally worth it, right? And then there's a group of people who says, well, okay, I don't find that to be so worth it. So what are other reasons that you could be doing it for? And I answered that question this way. In order for us to continue living on this earth as a species, we have to kind of not wreck it, right? And that apparently has started to be a little bit hard. And in order to do a better job as stewards of our planet, we need to understand better how it works and how the things that we're doing are impacting the climate, for example. And the climate is very complex, and it's very difficult to make accurate models that show you, A, what's going on now and how things are going to change over time. It's easier scientifically to be able to model something complex if you have other examples of it, so that you can make different models and see if your models predict the right things in very different examples. So when we look at Venus, for example, that's a great little microcosm of, well, not microcosm, it's a whole planet. It's a great example of runaway greenhouse effect, a planet that has these thick blankets of clouds that trap in heat from the sun and just make it really, really, really hot there. When we look at Mars, a planet that is a little bit farther away from the sun, it's actually at the edge of the sun's habitable zone. It's a bit smaller. It doesn't have much of a magnetic field. Scientists think it was warmer and wetter in the past, but it has lost a lot of its water, and what atmosphere it has seems to have leaked off into space over time. And so if scientists can understand what's going on in those two very different worlds, it helps them do a better job more accurately modeling what's going on with our own world. And that kind of thing, you really can't get any other way than space exploration. And there's plenty of other examples, like technology development that gets developed for space that ends up being very useful for people here on Earth, and various and sundry things.
Isn't it Tang because of NASA?
Yeah, I remember Tang as a kid too.
Isn't that
That's what I heard anyway.
I've got a kind of a little bit of a corollary question on top of that. Right before this, I do this little clubhouse chat thing on Fridays at 3. It's called The Future, Future Talk, cities, transportation, and other stuff. We were talking about one boondoggle of a project in California where I said for years that I've come up with a different way of approaching that project, where I think it would be a great test bed. It would lay out the future of driverless cars, driverless car technology, learning and transportation, and really like launch California and launch humanity into the next phase of the future of transportation. And somebody on the call brought up a great kind of analogy that I was like, oh, I got to bring this up on the call. They're like, yeah, that's a moonshot. Like your idea is so like out there. It's a moonshot, and that'd be great. That'd be so wonderful for the future of transportation. But how are you ever going to convince anybody to do a moonshot? And we were like, well, somebody convinced NASA to do the moonshot back in the past, and look at all the benefits that have come from that. So like when you're going to the people, or you're going to a government agency, and purse strings are tight, like how do you make a financial argument about the benefits of space or exploration?
It's really fortunate for me, right, as an engineer, that I wind up coming into the mix either after a mission has already been selected and funded, and then like, yes, give me my marching orders, we'll go get this thing done. But when I'm talking to people out in the general public, and I sometimes get people who come and ask me, look, point blank, like, why are we spending money on that? And they're not satisfied with my 2 answers that I gave before.
Exactly. That question. How do you answer that question?
Well, I tend to tell people to think about it this way. When they hear like this mission costs $500 million or that mission costs $1 billion, when you're thinking about your own personal finances, that seems like infinity. Like, well, why would you spend that kind of money that way? But I tend to think about it this way. Even for a mission that costs $1 billion, say, if every man, woman, and child in the country bought a cup of coffee from a coffee house, right? That would pay for that whole mission. There's like 350 million people in the country or so. And so when you think about it that way, or if, half the people in the country went to go see a movie, that would pay for XYZ missions. It starts to seem more, well, that's worth it. Like, let's all skip a coffee and go send a spacecraft to Jupiter, please, kind of thing.
You know what I think also is important is this is science education, because when you think about it with the purse strings, is that since we have a representative government, the higher educated and curious and excited about space exploration that you have the citizens, then they will elect people who then will also represent that interest. But that interest isn't going to be there if you're not, working with, high school and universities in order to kind of get that curiosity going.
That's an interesting
Partly
way
where
to think
the
about
chain of ideas. Yeah.
If a government official ever came to you and say, please tell me some kind of a benefit that I can go back to my constituents to keep you funded, how would you respond to that?
Yeah, so still happily above my pay grade, but I do know that there are people whose job it is to do those kinds of things. And like we mentioned a little bit earlier, the whole idea of technology transfer, things that get developed for the use in space. And there are, I think if you go and look for, if I can figure out the Google search terms, I think you can look for space technology transfer or something like that. And I think even every year annually is published a report of kinds of technologies that are developed for space that end up being really beneficial for stuff here on the ground. And there's something else that you said that made me remember back to your earlier question about how lessons that we've learned maybe we phrase it differently, in the kinds of job that I'm doing can be applied to real life, right? And I think about in systems engineering, when there's a problem that we're trying to resolve, the one important, really important thing is that we all have to come to the table prepared to understand the other person's perspective. So when we think about, like, again, I'm going to put on I'm not an engineer, let's pretend I'm a financial analyst hat, and are going into a room and people are arguing, should we spend money for space? Should we spend money for school? Should we spend money for food? And the answer is, yes, well, food, yes, school, those are important things. And I think that I would love it if people would approach this with the systems engineering perspective, which is maybe I'm coming in with my own personal opinion of what the answer is, but I really want to hear what you have to say, understand from your perspective why you're saying the things you're saying. I want to understand why you think you are right and try to figure out if there's something about what you're saying that will cause me to change my perspective. Because I think that too often when people come together, and especially talking about things that are very polarizing, like politics, like finances, like whatever, people tend to listen to the other argument, listening for the things that they will be able to beat down, right? I'm listening for your weak point so that I can attack it, which is not the best way to come to a kind of a consensus, as opposed to listening to what you're saying to see if there's something that I have never thought of before, if there's something that I haven't understood before. And even if that means at the end of the day, people are still going to be disagreeing, at least they will be more informed in their disagreement and not just knocking down straw men from the other side's point of view.
You know, something I think that can't be quantified, but is definitely a factor, is the morale. That, you know, just like recently with the news about Mars and seeing everybody jump up and down, and then everybody is so excited that it's not only the people who worked on it, but that's what I meant. Like at the beginning, this is a representation of what is possible for humanity. And I think that that's really important. So on that note, I want to ask you, how do you celebrate? What is it like? You know, we see the images on the news of people jumping up and down and being excited, but what is it like for you and for your team when there is a win on a project?
Yeah, and it's interesting because it's a little different if you are like personally involved in the mission, right? Because it's your own blood, sweat, and tears that got there, and it's such a huge cathartic release, like you climbed a mountain and now you're at the top, and it's amazing. Lots of jumping up and down, celebrating happening then. And even if you are like me, I had nothing to do with perseverance, yay, go colleagues. But it's still just to know that you are attached to a institution that has been able to accomplish something like that. You get a little of the backwash glory and you just feel really, really happy. It's that, I cannot pronounce that word, eudaimonia.
Eudaimonia, yeah.
Eudaimonia, thank you. It's that deep sense of accomplishment that is really hard to get any other way. And then, like, I think for the public, like my mom loves to watch these things, that even if, or now that we're all quarantined in our houses and watching it, there's still getting an opportunity to see the footage. I don't know how many of you or your listeners have watch the footage, like the cameras that showed looking down on the rover and looking up at the parachute. Like that was really new for us to be able to see. And it just makes you feel even more of a virtual presence. You feel like you are landing on Mars with the rover, which was really fantastic. And even though we can't go out and have a big party right now because COVID, it's still nice to just kick back and have a big smile and have whatever your favorite celebratory beverage is, like decaf coffee with coconut milk. It's nice to bask in that sense of human accomplishment.
Yeah. And it's historical. I mean, and it's also, like you said, it's a human accomplishment. It's for everyone. Do you have any thoughts about manned space missions, or what are the advantages to not having somebody on the mission or to doing robotics, or what are the pros and cons going on there? Are we going to have more people in space, or I don't know. So maybe with the cameras, is it necessary, or what are your thoughts on that?
Yeah, I'll just say that I know there are a lot of different perspectives out there. And to me, I think of them as just being different, right? There are things you can do with robotic spacecraft that, they can take a lot of extra G-forces. We don't have to send air and water, right? Mm-hmm. There are things you can do with robotic spacecraft that seem more straightforward to me, maybe just because that's where I have been working my entire career. And I do know that over time, people have gotten like the rovers, the orbiters, they have gotten a little more personified, and people are used to being involved in things at a distance, virtual presence kind of thing. And it feels a little more like we're all as humans involved, even if there aren't people there. But I also do think that there is an indescribable sort of intangible quality when there is a real physical human being that is out setting foot on another surface for the first time. And that's hard to quantify. And I think there's another level of attachment that people have, another level of involvement or excitement or pride or whatever when there are human boots on the ground somewhere. And I know it's true that humans have this innate ability to be flexible and be creative and innovate and problem solve and do all these things that is really hard to program into autonomous systems. We're getting better and better and better at that over the years, but I think there's always going to be a difference there too in terms of what humans versus robots can do. It just means different missions are appropriate for different of those things, or when you know you're going to do one or the other, that makes you design the mission a little differently.
Okay, Rudy, I'll yield to what you've been waiting to ask this whole time.
Here's the question that I really wanted to ask. As a result of the Mars reconnaissance mission, what did we learn about the climate of Mars from that mission? Are ideas of the climate of Mars change as a result of that? Because I know that was one of the points of that mission. Like, is Mars as uninhabitable as humanly possible? If
Rich Zurich or Stu Smirkar are watching this or listening to this, they're going to smack me because I'm sure they tried to tell me about this back when I was working on the mission. But be engineer, non-scientist. I can tell you some of the things that I personally remember being an engineer on that mission and hearing the scientists talk about what they were seeing, right? Because one of the things that I found just fascinating, and maybe this isn't necessarily a climate thing, but it's just a really cool picture, is that there are things changing on Mars on timescales that are human timescales, right? Like the high-rise imager took pictures of a particular area that had these geysers that were like shooting something, maybe CO2 gas, I don't know, out of the ground, and then depositing darker material onto the surface. And then as the spacecraft came by sometime later, they took another picture of that area. You could see more of those patterns. And so like geological changes still happening on Mars, super cool. There was another image that was taken near one of the cliffs along the edge of one of the poles, like the polar ice cap. And you could literally see huge clouds of dust as there was like avalanches coming down the side. Super cool, like stuff happening in real time that you could spot in these images. And I know that the instruments that were looking at like storms could see like these really interesting storms that looked kind of like hurricanes. I don't know what they were made of, like Rich or Sue can tell you. And so you can watch like real dynamic weather patterns happening. We know that there are dust storms that happen that can be global dust storms that cover the entire planet for days and days at a time, which is really cool. I don't know how much of that stuff the scientists already knew ahead of time, but those are the things that kind of stick out to me as an engineer, getting to ride along with the scientists and see what they were discovering that I thought were super cool.
As we both know, that was not the question that I wanted to ask, but that question did come up, and it's kind of a good segue into my question. And this is legitimate. This is not me trying to be funny. I'm being 100% accurate from the heart here, like I always am on here. I am afraid of alien life. I just am, period. When I read news stories or anything out there that even points to it, like I totally freak out about it. And there was this article, like, in our pre-interview, I was referring to an article that was in The Economist, and I've seen it elsewhere. But the one I'm referring to is from The Economist, that a distinguished astronomer sees evidence of extraterrestrial life. And there's this object that came, it starts off with the article, the object came hurtling in from deep space from the direction of Vega. It's a star 25 light years away across the orbital planet. And it was this object, you can search this online. It looks like a cigar flying in space, to be perfectly honest with you. And there's a well-respected astrophysicist at Harvard that is like, nope, I'm convinced that was definitely some kind of an alien ship that has come here and they're checking us out. And I have not been able to sleep properly in months. So please, tying this back into the Kepler question, you said billions of planets. You also, and the point of it was, hey, how many of those planets out there are kind of like Earth? Because Earth is the Goldilocks planet, right? It's not too hot, it's not too this, it's not too far away, it's not too close. It was the right place for this phenomenon called human beings, which, I'm convinced we're the only, beings in the galaxy because I'm arrogant and fearful. But you said there was dozens of other Earth-like planets out there. And that scares me because like I said, I'm afraid of alien life. So please help me sleep at night by telling me there are no aliens.
Okay, there's a lot to unpack here. But here we go. So it probably bears repeating, right, that the Kepler mission could kind of see whether things were around the same size as the Earth, and if they were within the right zone, that if there was water, it could potentially be liquid on the ground, right? That there's so many things that Kepler cannot tell about the planet. Can't tell if there's an atmosphere. Can't tell if there actually is water. Like, can't really tell exactly what the density is, though with follow-up observations, they can kind of get an idea. And so the couple dozen, go fact check the numbers, of planets that are in that maybe right size range, maybe right distance range, we still don't know if they are actually habitable, right? So if that helps you sleep, not a little bit. And so the second piece that I will say is, yeah, it really is truly phenomenal that there are just so many planets out there. But the thing that is also phenomenal in a way that is disappointing for people who really want there to be life forms that we can get in touch with is just the sheer distance that they are away from us. And I know when we talk about light years, it's hard for us to kind of imagine what that means. And so I'll throw out a couple of facts there, right? Our sun is about 93 million miles away from us. And the light from the sun takes about 8 minutes and 19 seconds to get here. If the sun blew up right now, we would literally not know about it for a little over 8 minutes because we would still be getting the old light until suddenly there was no light.
You just scared Rudy. Why did you say that? You just scared Rudy.
I mean, wait a minute. I thought I had at least another 4 billion years on this planet before the sun was going down. I'm definitely not sleeping for 4 billion years.
Face.
This is terrible. Please make me feel better.
It's still going to be like 4.5 billion years to the sun. Don't be scared. But if you try to drive in a straight line 93 million miles going 100 miles an hour, it would take you over 100 years to go that far. So like that's a long way in terms of the kinds of speeds we're used to thinking about in human scales. Now, a light year means you set light going, and instead of stopping it at 8 minutes and 19 seconds, just a measly 93 million miles, you let it keep going for more minutes and hours and weeks and months for a whole year. And that distance is a light year. Like, it is super far. And if that makes your brain melt, like it does my brain, you can think about it this way. The Voyager mission, the Voyager spacecraft, is traveling at something like 35,000 miles an hour. And if we were to somehow point it in the right direction to land in the right amount of time at where our nearest star system is, which is like 4 light years away, it would take 80,000 years to get there. And that's just 4 light years for our nearest star system if you could travel at 35,000 miles an hour, right? Now, when you think about the planets that Kepler has found, you'd have to go look up what the numbers are, but I think they're in something like 200 to 2,000 light years away, like really, really far in terms of anything we can make go at reasonable speeds from the technology that we have today. So it's not just that we're separated really far from these planets in space, but we're also separated really far in time. Like, our solar system has been around for about 4.5 billion years. And when you think about how much time there have been humans on the planet that have even had something as complex as radio to be able to beam things out even in all directions, not even aimed, right? Not even trying to include specific messages for aliens yet. It's a tiny, like ridiculously, almost infinitesimal fraction of the time that humans have been around. And we are perfectly capable of wiping ourselves out like any minute now. And so who knows how much longer intelligent life is going to be around on this planet. And so when you think about, is there a possibility for intelligent life to arise? How far away is it? Did it maybe arise and then kill itself off 1 billion years ago or 50 million years ago? Like, the timescales and the distances are so huge that even if there was the possibility for intelligent life to be out there, I personally am extremely pessimistic that we would ever actually cross each other like ships passing in the night. Forget it. I'm super pessimistic. So have a Coke, go to bed.
I will. I'm gonna dismiss. I'm gonna dismiss this cigar shape. I'm gonna dismiss this thing. I'm gonna be like, you know what? Tracy said this thing is way out there. I'm gonna dismiss.
I have one more thing to say about that. I'm glad you brought that up again, because the one thing to go back to the comment earlier about math is math, science is science, like there are things that are repeatable. One of the things that's beautiful about science is we make advances in knowledge because one science can do something, another science can do the same thing, and they'll get the same answer or a similar answer so that they can show, yes, I'm proving what you did. You can study a thing, someone else can study a thing and come up with the same thing. It works for stuff that we look at in space, for things that we look at underwater, microscopic things, like that's how science works. And the idea that there might be a single scientist who makes a conclusion about something and then like no other scientists agree, the way scientific progress works means that thing is probably not true. Now, when you look back in history, when like major advances are made, yeah, there might be a couple of lone voices crying in the woods, like the folks who determine the theory about dinosaurs being killed off by a big meteor impact, right? Everyone thought they were freaking insane, but people went off and started studying things. They were putting together evidence. There's that whole iridium layer between the KT boundary. If I didn't get that wrong, sorry, not a paleontologist. But there are ways that scientists could go out investigating whether those things that sound crazy at first are actually true or not. And when scientists do start to make discoveries, even though there might be some time lag to building scientific consensus around things, you're gonna hear about it, right? It'll be shouted from the rooftops, like, this thing happened, OMG. And when we get, if we get to the point when there's any evidence that really speaks to real, like, oh, there could be life forming out there, like, it's not gonna be like one person forever and you never hear about it again.
But what if I'm just throwing this out there, and there's philosophical, I'm serious about this. Just because truly, I don't think humankind, I'm not going to get into religious thought or anything. I don't know if religious thinking and the way that we've been taught theologically, I don't know if it could survive knowing that they're
it's totally connected.
I think it's mutually exclusive. It's mutually exclusive. That's my opinion.
From the time of Socrates' trial, he was accused of being an atheist. And the reason he was accused of being an atheist is because he was reading the works of Anaxagoras. And Anaxagoras was an astronomer, an ancient Greek astronomer. And so based on those grounds, he was charged with atheism. It would be like, so we still have this, from Galileo, right? Like, or even today when you're having discussions about genetic engineering and saying like, oh, no, don't do that. We still have, for some reason, when we're moving forward in science, that there are people who say, push back, you're not allowed to do that, but we still always do because we're just curious. But I was going to say, Rudy, wait until you hear about Brian Greene and that there is maybe a multiverse, that there could be a parallel universe of all of this happening right now. We're not just one universe.
Tracy, thoughts on that?
There's another one.
Please say no. Please say there's no alternate universe. I'm looking to you.
I got nothing.
Multiverse. That maybe one of our assumptions is that this is just one universe. That there might not just be a universe. This is string theory, though.
Tracy, do science engineers like you and your colleagues, do you guys have these discussions? Or do you think that philosophers and law people are the ones that are having these ridiculous, like, I'm fascinated. What do you guys talk about for fun?
Oh, we totally have these kinds of discussions, but usually just not when recorded. I don't want to be quoted. But it's really super fun, especially when you get like quantum theorists in a room with people who are studying dark matter. And the kinds of things that get discussed are like really, really mind altering. Lots of fun.
Well, I want to wrap up if we could. What would be some advice that you would give for future engineers, for mechanical engineers, aerospace engineers? What would you tell them that they should focus on? I know something in your TED Talk, you talked about success is working through failure, and I thought that was really great advice. But, what does the future hold, or what are you hoping with future engineers, and what could they learn from you, or some basic skills?
Yeah, so the one thing I really wish someone would have taken me aside my freshman year of college and said to me, I don't know if I would have listened because, 19-year-olds, come on, but I wish they had said, your goal in going through college to get an engineering degree is not to memorize as many equations as you can and to figure out how to solve the specific kinds of problems you have seen before later, right? Like that whole, do this problem, do a problem that's exactly like it, do a problem that's exactly like it. And when you get to work, you'll be doing the same, like, no, that isn't how it works. And in the real world, what you're trying to do is take problems that no one's ever solved before and figure out how to solve them. And therefore, the most important thing an engineer can learn, and I love that, I think this is true of philosophy too, you're there to learn how to think logically and to learn how to learn, so that you can be confronted with some brand new novel problem and figure out how to break it down into pieces, put together a framework of how to come at those pieces to get at a solution that makes sense. That's what engineering is all about. It's creative problem solving with the tools you have in hand. I think it's a little bit horrifying that the way we teach kids in college, that it's frighteningly easy to lose sight of that.
Hey, I totally
Tracy,
agree.
Really quick, I'm really sorry, but Gwen, Tracy, there's a major difference between engineering and philosophy, right? You guys get problems solved. You have numbers.
Did you notice?
In philosophy, there's no answers, right, Tracy?
No. Did you notice she said engineers and philosophers? The lawyers are there for when the problems go amok. They call the lawyer. We're like, we have this creative idea.
I feel this whole episode was against me and my fears and my insecurities. Whatever, Gwen.
So I'll make you feel better.
I'll make you feel better.
Problem. You want creative engineers? You've got a creative lawyer. It's like you're going to jail.
See, now here's the thing. I'm going to have to ask Gwen, and she'll have to lock you in a room or me in a room and educate us both. Because what I have absorbed about philosophy, right? Because sometimes we think about philosophy as people sitting around chewing on problems and just making up stuff and like, it could be this, it could be that, like it's all stupid. I don't think that's what it is. I think that philosophers, at least my vision of an ideal philosopher, Gwen, help me out here, is that you're trying to learn how to apply principles, a thought process. It's this, then that, right? There are the logical proofs, there's real progression, there's a structure to it, which is, I will grant you, not identical to the structure in math and science and engineering, but I think there's some overlap. There's this way of using your brain rationally that we don't always focus on teaching people to do, because it is a skill, right? And I think that all people could benefit from learning to think more like that. Like, I have an opinion, and my opinion is based on something, and let me articulate to you what it is. And when you can do that, that's when you actually make space for real discourse and an ability to change people's opinion. Because if you just come and say, I believe this because I believe it, and that's just the way it is, like, okay, well, we're done talking.
That's right.
We can't learn from each other.
When someone says that to me, that might be like the equivalent of someone saying to you that we never landed on the moon. That's my version of a flat earther. What you just said is like, I believe it and that's it. That's my version of the flat earther. But you're right. I mean, in philosophy, I say we're doing problem solving, but the problems that we're trying to work on don't occupy space. So if we were to have a discussion about this mug, it would be a very short conversation. We can use the 5 senses. If we're going to have a conversation about, is there justice and what is it? How do you define it? It doesn't occupy space. So it takes those if-then kinds of discussions, or what is the meaning of life? Like Aristotle coming up with the notion of eudaimonia, that doesn't occupy space. So you just have to think through, wait a minute, what are we doing everything for? What is anything for? And it's happiness, or eudaimonia. Happiness is a terrible English translation, but eudaimonia seems to be the only thing that is self-sufficient and for its own sake, that everything else is, that we do everything for. Yeah.
Nice. I love that. Can we do this every day? Oh, that's so much fun.
Hey, please come back on the pod. I would love that. And I'm sure that in the meantime, Rudy's going to have some more questions to ask you.
I'll go read that article.
Some more existential questions that he'll be asking from his couch. We're going to learn a little bit about, about aerospace and mechanical engineering, and then Rudy's fears.
Please. Oh my God. There's not enough time in the world. Tracy, if you read the article and you just email me, just tell me everything's going to be okay. That's all I need. I don't need anything else. I just need somebody to say everything's going to be fine. That'd be great. I'd appreciate it. By the way, I'd like to say the very first episode that we did with Gwen, we were introducing each other. She told me that she did this class about she taught ethics to engineers or something along those lines, and I made kind of a funny joke about do engineers even have feelings? Tracy, you have completely eliminated my ridiculous thinking because you have great feelings. You're a great person to talk to. This has been a lot of fun because the fact that you've even entertained my ridiculous fears means that you're a great, caring person. So thank you very much.
I feel like I did my good deeds for my week. Good thing, Rudy.
You did, Tracy. Thank you so much. And yes, absolutely, we want to have you back on the pod for sure. And I'm going to be sharing this with my engineering students. So thank you so much.
Absolutely. My pleasure. Thanks for having me.
Thank you so much for listening. If you have any questions about this pod, you can get in touch, goodisinthedetailspod@gmail.com, or we're on Instagram @goodisinthedetailspod. We're also on Facebook. If you're enjoying the show and you're listening on Apple Podcasts, please scroll down to the bottom and hit that 5-star review. And if you'd like to support the show, we're on Patreon at patreon.com/goodisinthedetails. Okay, until next time, bye.